Here, I've got an orange. So I'd like to measure, say, the radius of the orange, thinking of this orange as a perfect sphere. One way to do this would be to measure, say, the circumference of the orange around its equator. So here, if I measure that, it looks like it's about 24 centimeters. So the circumference of the orange is 24 centimeters. What does that tell me about, say, the radius of the orange? Well, that circumference will be 2 pi times the radius of the orange. So if I divide both sides by 2 pi, I get that the radius of the orange is about 12 over pi centimeters. How much rind is there on this orange? That can be formulated as a linear approximation problem. Well, let's set this up. So I just calculated the orange radius to be about 12 over pi centimeters. I want to figure out how thick the rind is. Let me peel off a bit of the orange here. I just want to measure how thick this is with, say, my little ruler here. And yeah, maybe 3 millimeters. So 0.3 centimeters will be the rind thickness. Now, how does knowing the rind thickness going to help me to calculate, or at least approximate, the volume of the rind in this whole orange? Well, I know the volume of a sphere, which is what I'm modeling the orange to be, is 4/3 pi r cubed, and the rind volume is at least approximately how much the volume changes when I take this formula and replace r with r minus h. Right? When I take that sphere and I make it just a little bit smaller, that change in volume is the volume of the rind. Now, to understand how wiggling the input affects the output, I'm going to use the derivative. The formula that I want to be differentiating here is this volume of a sphere of radius r, which is 4/3 pi r cubed. And if I differentiate this with respect to r, the r cubed differentiates to 3r squared, and the 3 in the denominator here will cancel this 3 by the power rule, so the derivative will be 4 pi r squared. Now what I'm trying to approximate is the rind volume, which is really the difference between a sphere of radius r and a slightly smaller sphere where I've shrunk down just past the rind, right? That difference will be the volume of the rind, and approximately this is h times the derivative of v at r, right? Because this is asking how does the output change when the input goes from r minus h to r, and it's approximately the input change times the derivative. Now in this case, what do I know? The orange's radius is 12 over pi, so I'll use that for r, and the rind's thickness is 0.3 centimeters, so I'm going to use that for h. So this is 0.3 centimeters times 4 pi times this radius, which is 12 over pi centimeters squared. So this is cubic centimeters. Well, that's good because I'm trying to calculate a volume. And I'll just keep calculating here. So it's 0.3 times 4 pi times 144 over pi squared cubic centimeters. And 4 times 144 is 576 times 0.3. The pi divided by the pi squared just gives me a pi in the denominator. So I got 0.3 times 576 over pi cubic centimeters. That's about 55 cubic centimeters. So the volume of the rind is approximately 55 cubic centimeters. Now, admittedly, I could have calculated the volume of the rind just by calculating the volume of the whole thing, calculating the volume of the whole thing with the radius reduced by h, and taking a difference. But the neat thing here is that you can approximate that quantity by using calculus, right? By thinking about this linear approximation business. I also want to see now how close the linear approximation was, right? So I've taken my orange and peeled off all the rind, and I've taken the rind and smushed it down into this ball, and I'll try to calculate the volume now of this rind ball. I want to compute the volume of rind, and I made that rind ball here. Let me compute the circumference of this rind ball. It's about 15 centimeters. So the circumference of my ball of rind is about 15 centimeters. That means my rind ball has a radius of 15 over 2 pi centimeters. And here, assuming my rind ball is a perfect sphere, this will be the volume of the rind ball. But in here, I got to put the radius, which is 15 over 2 pi, so 4/3 pi, the radius cubed. And that's about 57 cubic centimeters. So yeah, I mean, I actually took all the rind off the orange, and the value that we got is pretty close to what the linear approximation told us the volume of rind should be. This perspective sheds some light on what might otherwise be seen as just some random coincidence. Now what you notice is that the volume of a sphere, which is 4/3 pi r cubed, and the surface area of a sphere, which is 4 pi r squared, these two formulas are related, right? If I differentiate this volume formula with respect to r, I get the surface area formula. Again, we're seeing that calculus isn't really about solving specific problems. I don't care about the volume of the rind of this orange, right? If that was what calculus was good for, who would care, right? What calculus is really good at is providing a general framework, and with that general framework we can begin to see the patterns between different concepts. Like this fact that the surface area of a sphere is the derivative of the volume of a sphere with respect to the radius, that's not really a coincidence, right? Calculus is providing an explanation for that supposed coincidence.